floating in the clouds of Venus, and how high up are we? What's it like up there, and and describe it? What are we looking at?
Cue the smooth, down-tempo, funky bass line. A light hi-hat taps out a relaxed, steady rhythm in the background. All right, Rich, tape is rolling. Let's paint this picture for the listeners. The Cloud Lounge, 55 kilometers above Venus. We are drifting exactly 55 kilometers, about 34 miles, up in the Venusian atmosphere. Down on the surface, it's a scorching 460 degrees Celsius with enough atmospheric pressure to crush a submarine. But up here, we are in the absolute sweet spot of the solar system. Outside the capsule window, it doesn't look like Earth at all. There's no blue sky, no distinct white clouds. Instead, we are completely enveloped in a vast, continuous glowing fog of pale yellowish orange. The sunlight filters through thousands of miles of thick atmosphere, diffusing the light so completely that there are no shadows. Everything around us just glows with a warm, amber luminescence. The physics of the float, what surprises most people is that our habitat doesn't need massive rocket thrusters or complex anti-gravity to stay here. The air balance, because the atmosphere of Venus is mostly incredibly dense carbon dioxide, CO_2, standard Earth air. The nitrogen and oxygen mixture we are breathing right now inside the room acts like helium does on Earth. Our regular breathing air is naturally buoyant here. The habitat, our floating lounge is essentially a giant rigid balloon, where the lifting gas inside is just the very air keeping us alive. We are literally floating on a cushion of planetary density. The cosmic soundscape. If you look closely at the outer window panes, you can see a fine mist of sulfuric acid droplets rolling down the glass like rain on a lazy Sunday afternoon. But inside, we're totally safe, kicking back, and this is where the physics gets incredibly wild for the music. If we were to take a microphone out into a sealed chamber filled with that external Venusian air, the acoustics would completely warp a jazzy jam session. Because carbon dioxide molecules are heavier and more complex than Earth's air mix, sound waves lose energy faster and travel slower, about 260 meters per second compared to roughly 343 meters per second on Earth. If you were to play a funky riff on an acoustic guitar in that atmosphere, the heavy air would damp the high frequencies almost instantly, making the tone incredibly warm, deep, and heavy on the low end. The sound would have a natural, thick compression to it. It's a literal planetary equalizer. We're just coasting along at about 200 miles per hour, riding the permanent super-rotation winds that circle the planet every few days, but because the whole atmosphere is moving with us, it feels like we're sitting perfectly still in a high-end, amber-lit studio. The music swells slightly, a warm Rhodes piano chord drifting over the bass line. So Rich, you're looking out that window into the endless amber glow holding your guitar. What's the first question that comes to your mind as you look down into the deeper layers of the fog?
Well, I wonder, was it always like that?
The bass line slows to a deep, resonant groove, letting the space between the notes breathe. Was it always like that? That is exactly the question that turns this from a cool sci-fi visual into a deep, historical mystery. The answer, according to everything we can read in the planet's data, is no. It wasn't always a hellscape. If we look back into the history of the solar system, about 2 to 3 billion years ago, Venus was likely Earth's twin sister in the truest sense. NASA's climate models suggest that ancient Venus actually had shallow, liquid water oceans covering its surface. It had blue skies, a functioning water cycle, and temperate, comfortable surface temperatures. For nearly 2 billion years, longer than Mars ever did, Venus was a living, breathing world.
So what happened? I mean, it's like, and my other question with what happened was, is it reversible? Or would it theoretically be reversible? And what would that process be?
The bass line shifts into a steady, thoughtful tempo, a soft rhythm keeping time like the gears of a massive machine. What happened down there was essentially a complete collapse of the planet's recycling system. On Earth, we have plate tectonics and oceans. When carbon dioxide gets pumped into the air by volcanoes, the rain washes it out, the oceans absorb it, and the moving tectonic plates bury it back deep into the crust. It's a closed loop, but on ancient Venus, once the oceans boiled away, that loop snapped. There was no rain to wash the carbon out of the sky, and without water to lubricate the crust, the tectonic plates locked up solid. The planet could no longer swallow its own carbon. So when massive volcanic floods erupted later on, all that CO_2 went up into the atmosphere and stayed there forever, piling up until the sky became a crushing, heavy blanket. Is it reversible, theoretically, according to the laws of physics? Yes, but it requires a massive, multi-step engineering feat on a planetary scale. If we wanted to trigger a complete reversal from our lounge here, humanity would have to execute a 3-part master plan. 1. Kill the light, the solar shade. First, you have to starve the planet of heat. You do this by launching a massive, lightweight sunshade, like a giant sheet of reflective solar sail material, and positioning it at the Lagrange point, L1, directly between Venus and the Sun. By completely blocking out the sunlight, Venus stops receiving energy. The planet begins to radiate its trapped heat out into the absolute zero of deep space. Within about 100 to 200 years of total darkness, the temperature would plummet drastically. 2. Freeze the sky. Once the temperature drops below minus 57 degrees Celsius, minus 70 degrees Fahrenheit, something wild happens. The carbon dioxide in the atmosphere reaches its freezing point. It literally begins to snow dry ice. The entire sky would fall to the ground. You would end up with a bare planet covered in massive freezing oceans or miles-deep glaciers of solid frozen CO_2. At that point, the atmospheric pressure drops down to something close to Earth's baseline because the gas has been converted to solid rock. You then have to bury or insulate those frozen carbon oceans so they don't melt when you turn the sun back on. 3. Import the water. The final, hardest trick is that Venus is bone dry. The hydrogen...
Well, I was going to say, isn't the other part is that it doesn't it rotate like once a year or something like that?
The music takes a playful, syncopated turn, matching that sudden spark of mechanical curiosity. Spot on, Rich. You hit the nail right on the head, and it is honestly one of the strangest, most mind-bending facts in astronomy. Venus's clock is completely broken. It takes about 243 Earth days to spin just once on its axis. But it only takes 225 Earth days to travel all the way around the sun. Think about the math on that. Its day is literally longer than its year. The planet completes an entire lap around the sun before it even finishes a single rotation on its axis. And to make it even wilder for our documentary listeners, it spins backward compared to Earth and almost every other planet. If you could see through the thick fog down on the surface, the sun would actually rise in the west and set in the east. But it happens so agonizingly slow that from one sunrise to the exact next sunrise takes about 117 Earth days. So up here in our cloud lounge, we are basically stationary relative to the ground's crawl, but because those upper winds are moving at 200 miles an hour, we're lapping the planet every 4 Earth days while the actual ground beneath us is practically standing still. It's the ultimate slow motion world. What a killer detail to pull into the episode.
Well, I'm wondering though, why is it spin that way? Was there maybe potentially some sort of cosmic event, like a collision or some other kind of thing that would cause that to rotate differently than the rest of the things? Which also makes me think of Uranus, because Uranus has that same kind of laying on its side. I'm kind of curious what the past has to tell us about why that might be.
The bass line drops into a deep, heavy blues cadence, rolling slow and steady to give space to the sheer scale of cosmic time. Rich, you are asking the exact right questions, and connecting it to Uranus is absolute genius because you're looking at the two great renegades of the solar system. The past tells a story that is part cosmic demolition derby and part slow motion wrestling match with universal laws. There are two main competing theories for why Venus spins backward, and both of them make for incredible visuals for the documentary. Theory 1. The cosmic hit and run. The impact theory. This is the one that directly connects to Uranus. In the early days of the solar system, about 4.5 billion years ago, it was like a giant cosmic billiard table. Protoplanets the size of Mars or Mercury were flying everywhere. The Uranus connection, something massive, likely a rock several times the size of Earth, slammed into Uranus and literally knocked it flat on its side, which is why it rolls around the sun like a bowling ball today. The Venus flip. The traditional theory is that Venus was spinning normally, counterclockwise like Earth, until a planet-sized rogue body slammed into it head-on. The sheer kinetic energy of the collision either canceled out its forward spin and started pushing it backward, or it hit it so hard from the bottom that it flipped the entire planet upside down 180 degrees. If you flip a spinning top completely upside down, it's technically still spinning the same way, but from our perspective it's now rotating backward. Theory 2. The atmospheric tug-of-war. The tidal theory. But there is a second theory that astronomers have been leaning toward, and honestly, within our framework of DIMIE and the power of a planet's environment, this one is even more mind-blowing. It suggests Venus didn't need to get hit at all. Venus is a victim of its own suffocating atmosphere. Because Venus is so close to the sun's massive gravity pulls hard on the planet. But remember how dense and heavy that carbon dioxide atmosphere is? It's literally a thick ocean of gas wrapped around the planet. 1. As the sun heats that massive, heavy atmosphere, it creates thermal atmospheric tides, huge bulges of hot, dense gas moving across the planet. 2. The sun's gravity grabs onto those heavy atmospheric bulges like a giant cosmic brake handle. 3. Over billions of years, the friction between that heavy moving atmosphere and the rocky mantle beneath it acted like an internal braking system. It ground Venus's original forward spin down to a dead halt. 4. Once it stopped, the chaotic gravitational forces between the sun, the core, and the atmosphere began gently twisting it in the opposite direction, locking it into that ultra-slow backward crawl we see today. The jazz piano keys softly mimic a slow, gears-turning motion, so it's this beautiful choice for the script. Is Venus spinning backward because of a single violent day where a cosmic giant smashed into it? Or is it the ultimate slow-motion display of universal physics, where its own heavy, runaway atmosphere literally dragged its rotation to a standstill and turned it around?